Yesterday I talked about to graph or not to graph, and I discussed two approaches. One of them is to use a graph, which is just a way to connect processors together to transform a piece of data. And then I also showed you can do the similar thing in another approach with ECS, but it gives you the problem of you have a linear system design, so you have all these systems playing out in order. You can change the orders or remove one or add one, but you do get very good performance because you have the cache locality, the contiguous layout, no multiple loops per graph, no graph traversal. So the ideal setup, you would have the type of graph idea where you can design the processor pipeline, but you don't have the issues of the of the traversal and of the memory layout. Now, the solution to that is to actually be able to compile the code directly. So if, for instance, you have all these plugins in FL Studio and they're all doing some transformation with your sound buffer, if all of that was directly compiled to code instead and then run, you have one loop, you have one buffer that you're using, and you have one call. And you can do that with the lambda expressions here in C#, for instance. You can design dynamic code and then compile it so it's turned into this intermediate language or bytecode. I don't know which one it is, but it's the same performance as native code. And you basically have a function, a dynamic function. Now, the way I've set it up here is it's not the best. I've been experimenting with it because it turns out it's actually pretty... you really need to sit down and learn how to write this because I don't think I've done it that optimally. But I have a basic example here. This is a compile function. It creates a kernel. This is all just a name. Basically, we're just writing this delegate function dynamically. And we pass in the buffer. The context is not relevant. And then we generate the for loop. Now, you can see here the output of it. You can see it's a lambda function. It takes in these parameters. And then it goes over the buffer here in a very primitive loop. And then it calls these transformation functions. Now, the interesting thing about this is if you go to the actual implementation of it, these are just transformation functions I just copy pasted and I changed some of the constants of. But what it shows you is that ultimately any signal processing is just transforming or adding or removing the data. So if you could just represent these as little modules, then you could copy paste the module code inside of a new function and you would have the same speed as if you just wrote the entire function yourself. It does get a bit more complex because you still need to add the parameters. You need to make this larger, more abstract system that combines all of the parameters inside of it, and you need to make sure that you don't recompile unnecessary functions because what is the point of that? What is the point of recompiling the entire function if you can just recompile tiny bits of it and just swap it in? So the idea of it is very simple, but the implementation is a bit more difficult. But this solves the issue of having graphs, but not fighting the idea of traversing graphs, because you're not really traversing the graphs every time you're processing the signal. You're just traversing it when you're building out the final transformation function. I don't know how many digital audio workstations use it. As far as I know, FL Studio doesn't. I don't know if Ableton does because I don't know much about Ableton, but this is ultimately the fastest way to do audio processing, with the exception of, and this is just unrealistic for normal people, normal developers, to send off these tiny kernels like the way you would send off a shader to a dedicated signal processing hardware. I don't even know if we have these, but maybe we do. So for you, as a normal developer, this is probably the most complex thing you're going to be making, to combine all the cool things about being able to have dynamic transformation to your process, to your signals, but not having any of the constant issues of managing the memory and the graphs, etc. Now here, down here, you can see the output, but I don't think it's that particularly interesting. What's mostly interesting is looking at the lambda function itself. You can see that instead of having a loop for every single one of these, we just have a single loop, and it basically copy pastes the transformation in there, and that's really all you need.